Okay, so this is number 10 on the team test. So we have a concave hexagon A, B, C, D, E, F, and as given. And A, B, and E, F are parallel. So we are told this is parallel to this guy. And the B, C, and D, E also. So these guys are parallel. And then angle sum for A, B, C. So the angle A right here, B and C add up to 270. What's the area of the figure? Okay, so it's quite challenging because there are too many given info, but at the same time, it's not really easier to see where to start with or how we can use those information, right? So one of the things that I kind of like to start with, the angles. Like we have the angle sum, so which is 270. I feel like this is like 360 minus 90 is a nice number. So maybe we can just make a quadrilateral because that's the angle sum inside of the quadrilateral is 360. So we can get a 90 degrees, which is going to be a good triangle. So just imagine the angles C, B, and A. If you make the four-sided figure, so this is 1, 2, and then maybe extend this way so we can kind of get the angle. So that is my first step. So I'll try extending DE. Okay, so as much as I need, and then AF as well. So they will intersect at some point, and the intersection should be 90 degrees right here. Because we know the angle A, angle B, and angle C add up to 270. So to get 360 should be 90. So which is a good promising point because whenever you have 90s, it's kind of nicer to have because it has a lot of power. So what I'm going to do, I'm going to connect these two because right triangle is good to have. But we never use the given information about the parallel lines, right? So maybe we should include those as well. And one of the things that we kind of need to keep in mind, whenever you are given some parallel lines, then hunt for some similar figures, right? So that's why maybe you can extend the FE, but when you do so, you probably need to extend this as well. So you can get this triangle to be similar to the larger one and stuff. Or we can extend this way so we can get some parallel stuff going on. But let's go ahead and extend first just to see if that will give us something nice. Okay, so if I extend DE until it just hit the AB, and then if I extend FE until it hits BC at some point, okay, let's label those. I'm going to call this intersection A, let's say K. And then I'm going to name this is L, this is M, okay? So we know that the angle B is congruent to angle at B right here because AB and FM is parallel. So these two are corresponding angles. And the same idea, so since DE and BC are parallel, so this angle has to be corresponds to this angle, so which is why they are also congruent. So we can say this is also same as those angles. But what else, right? So we know that angle C, I'm gonna use different notation. So this angle has to be same as the angle right here because these two angles are corresponding since these two are parallel. So I'm gonna actually shade this in full red. So the angle D right here and the angle C right here are congruent to each other. So, but I want you guys take a look at the figure now. I think we have something nicer. So the KDEF, this quadrilateral has this angle, and 90 degrees is congruent to similar to the triangle, like the quadrilateral is similar, but the angles are congruent. KCBA. So let me write that. So the quadrilateral KD, like EF, is similar to KCBA. KCBA by angle, right? So they are similar because the angles are equal. So this angle corresponds to C, K corresponds to itself, and F corresponds to this because we know these two are parallel. So maybe I should have said earlier, but those are also like congruent. So this guy right here is the same as this guy. Without really saying this, we can say because other three are equal, so the fourth has to be same. So now we have these are congruent, so I mean similar. So if they are similar, right, let's write the ratio. And also, 34 and 51 was good numbers because they are both divisible by 17. So then DE is the corresponding side with BC, CB in the larger quadrilateral. So we can write the ratio as 34 over 51, and that is just 2/3, and that is equal to FE, which is 16, corresponds to AB, so which is 24. As you see, these two are actually both 2/3, which is promising. And if I name this guy to be A, and then this is B, so this KF is my one side that corresponds to KA, which is A plus 9. And similarly, DB corresponds to B plus 12. I think we had everything so far. So we have 1, 2, 3, and 4. So from here, so the ratio is 2/3. So if I take the 2/3 equals A over A plus 9 and do cross multiplication, that's 2A plus 18 equals 3A. A will be 18. And use the same thing with the B over 12. So then will give us B as 24. So let's write that 24. And 18. So we know this is 6 times 3. This is 6 times 4. So that means hypotenuse 6 times 5, which is 30, which is nice. And also, like, you could have just guessed that, because if you couldn't really see immediately, you can always go ahead and guess some triples, because this is 8, 15, and 17 triangle as well. So which is why there is a right angle triangle here. But we already know this is 30 because of this triangle. So that will tell us this is also right triangle. Okay, so far so good, right? So we have a lot of information already. So what we want to find is the area of the given original, like the hexagon. So, but we know this region, and this region is not really fun to find the area for because we don't really know these pieces. Maybe we can use the similarity relation with the areas, right? So we know this smaller quadrilateral, we can find the area of this quadrilateral, which is like 18 times 24 over 2 plus 30 times 16 over 2. So that should be 18 times 12. And then like 30 times 8. So we can just go ahead and multiply these guys. So I'm going to multiply by hand. So 18 times 10 is 180. And then 2 times 18 is 36. And then that's 340. So if I add 240 to 200, that will be 440, but 20 lesser, but 16 more from here. So that will be 400, I guess, 56. I hope I didn't miss anything. So the area of the smaller quadrilateral, like KDEF, is this much. So since the ratio was 2 over 3, so if you remember, when you have two figures that is similar, the area ratios is the square of the ratio of the similarities. So if you square this, that will be equal to area ratios of those. So that will be 4, 5, 6 divided by the area of the larger quadrilateral. So if you solve this equation, so you will get 4 over 9. So if you do cross multiply, 4a equals 9 times 4, 5, 6, and divide by 4. So the 9 times, like 44 divided by 4 is 11. So you will get 16 left over. So that should be 114 times that. And the area is equal to 900 plus 90 plus 36, which is equal to 1226, I guess. Again, this is not what we are looking for. This is the area of the larger quadrilateral. So we have to subtract now the smaller one, which we already know the 4, 5, 6. So 1226 minus this guy. So let me double check if I did something wrong. Okay. So we had those areas, right? So let me subtract and see. So that is 0. So that is 7. 11 minus 4 is 7 as well. Okay, I think I missed something. So let me check this part. So 2/3 squared was 4/9. So 9 times this equals 4 times this. When you divide by 4, you get 111. That's 4, 990 and 36. So that should be 990. Oh, this was wrong. So the answer was like 990 plus 36, which is 1126. I just use manual adding, so that's why you should check with the calculator because this is on the team run. So that means 1126, so that should be 0. And that's 12 minus 5 is 7. So that should be now 10 minus 4 is, oh, this was this 0, right? Okay, as you see, I'm just doing this a lot of mistake. Okay, so anyway, so this is gonna be 570. So again, I do know the answer because I checked the answer key. But I hope that was clear. So this is, to be honest, one of the best questions I ever seen for this year. So it was nice to use the similar figures in some regions that we actually don't expect to see similarity. But the key point was the parallel lines. Okay, so whenever you are given some parallel lines for some 90 degrees, so it's good to hunt for some similar figures. Okay, I'll see you in the next video.